In Chapter 5, the topic is ferrous metals and alloys. Ferrous metals and their alloys are most widely used materials. This is because of their properties, their performance, ease of manufacturing, and low cost. We're gonna take a look at the iron and steel production from ore. We will describe furnaces and foundry operations. Casting of ingots is described in this chapter. Properties and applications of ferrous metals are discussed. We're gonna learn about cast iron, carbon and alloy steels, high-strength steels, stainless steels, and tool and die steels. So due to their low cost and wide range of properties, ferrous metals and alloys, they are among the most useful of all materials. So when we say ferrous metals and alloys, you guys understand iron is the base material. We can classify ferrous metals and alloys as carbon and alloy steels, stainless steels, tool and die steels, cast irons, cast steels. So steel is a ferrous alloy, and it is basically a mixture of iron and carbon. And of course, it also has other type of alloying elements to basically achieve certain type of properties. Ferrous metals make up 70 to 85% by weight of structural members and mechanical components. So where do we use ferrous metals and alloys? As sheet steel for automobiles, plates for boilers, ships, bridges, structural members such as I-beams, railroad rails, tools, dies, molds, fasteners such as bolts and nuts. So when we look at the production of iron and steel, there are three basic materials used in iron and steel making. These are iron ore, limestone, and coke. Well, iron is one of the most abundant elements in the world. It is making up about 5% of the Earth's crust. So when we say iron ore, these are basically where the iron is coming from, right? These are taconite, as seen in this image, hematite, here, it is an iron oxide mineral, and limonite, like we see here, that is an iron oxide containing water. So of course we get this from Earth's crust, and now next, of course, we need to at the end purify this and get the iron itself, right? So it has to go through certain processes. So after it is mined, the ore is crushed into fine particles. Impurities are removed, such as the one technique can be magnetic separation, and the ore is formed into pellets, balls, like in this image we see, and with using water and some binders. And typically the pellets are about 65% pure iron and about 25 millimeter in diameter. Limestone is basically calcium carbonate, is used to remove impurities from molten iron. So basically the limestone reacts chemically with impurities, and this acts like a flux and causes impurities to melt at a low temperature. Therefore, combining limestone with the impurities, this is what we call forming a slag. Slag is light and it floats over the molten metal, and this way we can remove it. So what about Coke? Of course, it is not the drink. It is actually, think about it as fuel. Okay, fuel that is necessary in iron making. So Coke, basically a soft coal, and that is heated in vertical ovens up to temperatures of 1150 degrees C, and then cooled with water in quenching towers. So what are the functions? Why do we need coke in iron and steel making? Because it has several important functions. The first of all, it will generate high level of heat that is required for chemical reactions to take place, right? In iron making, there are several chemical reactions that needs to take place. And also it produces carbon monoxide. Carbon monoxide is a reducing gas, which means it will remove the oxygen. For example, it will remove the oxygen from iron oxide, which will reduce into iron. That is what we want, right? So therefore it will be used as a fuel basically, and it will be reducing the iron oxide to iron. So that's its function. I suggest you guys watch the videos also that I gave you the links of in Canvas. You will see, and then you should watch those too after you listen the lecture, because that way it will make more sense. You will see the terms I described here, and you will be able to understand how in real life what they look like basically. So those three raw materials, iron ore, limestone and coke, basically dumped into the top of a blast furnace, and with an operation called charging the furnace. So what is a blast furnace? It is basically a large steel cylinder here. It is lined with refractory brick. Refractory means, here you can see, it is a ceramic, it's a brick, and it can resist up to very high temperatures. The charged mixture is then melted in a reaction at about 1650 degrees C, okay, with the air preheated to about 1100 and blasted into the furnace. That's where the blast term comes from here. Through nozzles called tuyair. Okay, so several reactions take place, but what is the most important and the basic reaction there is happening? It is the oxygen combining with the carbon and producing carbon monoxide, which of course, as I described, from the reducing iron oxide to iron. That's the main reaction that is taking place. So preheating the air is necessary because even the coke is the fuel here. It might not provide the sufficiently high temperatures for the reactions to take place. Molten metal accumulates at the bottom of the blast furnace, while the impurities float on top. So at intervals of 4 to 5 hours, the molten metal is drawn off into the ladle cars. Okay, ladle cars, and they can hold as much as 160 tons of molten metal. And molten metal, we call the molten metal that is at this stage is pig iron or simply hot metal. And the typical composition is 4% carbon, 1.5% silicon, 1% manganese, 0.04% sulfur, and 0.4% phosphorus. So the rest is, of course, iron. So when it comes to steel making is nothing but refining the pig iron. Okay, so how do we refine the pig iron? What does it mean? It means, of course, reduce the percentages of manganese, silicon, carbon, and other elements. Control the composition through the addition of various elements. So you can remove some elements, add some element based on what type of desired property you want to get, because there will be different type of steels, right? And you can adjust the composition by adding the elements and removing some of the elements. And this is done after the pig iron is obtained. This is done when the pig iron is transported into one of 4 types of furnaces: open hearth, electric, vacuum, and basic oxygen. Open hearth is basically using flames to melt the metal. And this furnace has now been replaced by electric furnaces and basic oxygen process, which are more efficient and producing better quality of steels. So when we look at electric furnace, of course, as the name implies, the source of heat in this type of furnace is continuous electric arc formed between the electrodes and the charged metal, and temperatures as high as 1925 degrees C are generated in this type of furnace. Usually there are 3 big graphite electrodes. Okay, I suggest you guys watch the videos I send you in Canvas. So big, large graphite electrodes, and in between those electrons and the charged metal, the electric arc is formed and high temperatures are obtained. Together with the pig iron, steel scrap and small amounts of carbon and limestone, they are dropped into the electric furnace through open roof, and the roof is then closed and electrons are lowered. The power is turned on, and within 2 hours the temperature increases to a sufficient levels to melt the metal. And the current is then shut off, the electrodes are raised, the furnace is tilted, and the molten metal is poured into ladle from here. Okay, so remember, when we say ladle, this is basically a receptacle used in transferring and pouring molten metal. Okay, we will use the same terminology over and over again. Furnace capacity range from 60 to 90 tons of steel per day, and the quality of steel produced is better than that of from open hearth and basic oxygen process. Of course, there are other type of configurations that you can achieve, but the basic principle is the same. For smaller quantities, electric furnaces can be of induction type, like this one you are seeing. The metal is placed in a crucible, a large pot made of refractory material, and surrounded with a copper coil, which the alternating current is passed through, and therefore it induces a current, and this generates a heat and melts the metal. So we talked about this, that, and the vacuum furnace. So vacuum furnace is similar to the induction furnaces, but as the name implies, right, vacuum, the air has been removed. So the cooling is also achieved using an inert gas, and this way we can remove the gas impurities from the molten metal and we can prevent oxidation. Therefore, vacuum furnaces produces high quality steels. So basic oxygen furnace is the fastest and by far the most common steel making furnace. 200 tons of molten pig iron and 90 tons of scrap are charged into a vessel. And next, fluxing agents such as lime, fluxing agents such as calcium and magnesium oxide, they are added. And the reason why this process is called basic, because of the pH of these fluxing agents. And then the pure oxygen blown into the furnace through a water-cooled lens, which is a long tube. The agitation of the oxygen refines the molten metal by oxidation process, by which the iron oxide is produced, and that oxide reacts with the carbon, which produces carbon monoxide, carbon dioxide. Then the lens is retracted and the furnace is tapped by tilting it. And the slag, the impurities of course, okay, so they are removed by tilting the furnace in the opposite direction. Next is casting of ingots. So steel making process involves shaping of the molten metal into a solid form, which we call ingot, for further processing. Okay, these are ingots. So ingots actually used as we roll them into shapes or casting into finished products or during the forging. So how do we obtain the ingots? The molten metal is poured from ladle into ingot molds, and then which it solidifies. The cooled ingots are stripped from the molds and then lowered into soaking pits. As you can see here, they are lowered into soaking pits. Let me write it down. So why do we do that? Because we keep them before they are further processed, like maybe before they go to forging, rolling, we keep them at a uniform temperature. So everywhere in the part has the same temperature, uniform temperature of 1200 degrees C. They are kept at temperature, so everywhere in the material has the homogeneously distributed structure before it can go into further processing like rolling and forging. So of course, during the solidification of an ingot, many reactions will take place, which can affect the quality of the steel, that is produced. For example, gases like oxygen or other gases can dissolve in the molten metal. And of course, when it is solidifying, these gases are rejected because they have a solubility limit of these gases in the metal. So these gases can cause porosity in the ingot because the rejected oxygen from the structure can combine with carbon and can form carbon monoxide. Of course, when this is stuck inside, it can show itself as porosity in the structure, in the ingot. So, therefore, depending on the amount of gas evolved during solidification, 3 types of steel ingots can be produced. Okay, one is killed steel, semi-killed steel, and rimmed steel. Killed steel is fully deoxidized. The oxygen is removed and associated porosity is therefore eliminated. So, in this deoxidation process, oxygen dissolved in molten metal reacts with elements such as aluminum, silicon, manganese, vanadium, and that had been added previously to the molten metal. Since these elements have an affinity for the oxygen, they react with the oxygen in the metal, molten metal, and they form metallic oxides. And of course, these are then removed with the slag. Killed steel is also free of any blowholes. These blowholes are large spherical holes near the surface of the ingot. So I got you an image here and how they look like in the surface of an ingot. This is how blowholes look like. In killed steel, it is free of any blowholes. However, of course, going from a liquid to solid, there will be shrinkage in the structure. And because of this shrinkage, the ingot will develop a pipe at the top. We also call it shrinkage cavity. It is with the appearance of a funnel-like shape. You can see it here in this image. Okay, this pipe formation because of shrinkage, basically. So we can add this one also. So semi-killed steel. Okay, so as the name implies, here we have a partially deoxidized steel. So it contains some porosity, but it doesn't have pipe formation because basically the piping is offset by the presence of porosity at the upper region. So we can say there are porosities but no pipe formation. And this is economical to produce semi-killed steel. So partially deoxidized steel. What about rimmed steel? So it is only partially killed by adding elements such as aluminum. Aluminum, as we talked, reacts with the oxygen, form metal oxides, and these are removed with the slag. And the gases produce blowholes along the outer rim of the ingot. That's why we call it with the term rimmed steel. Okay, so there are blowholes forming along the outer rim of the ingot. And again with the same idea, rimmed steel don't have little or no piping, and they have a good surface finish and have a ductile skin and a carbon content that is less than 0.15%. So what is refining? Of course, refining is removal of impurities, inclusions, or other elements from the ferrous alloys, right? And this will of course affect their properties. And most refining is done in melting furnaces or in ladles. This is achieved by addition of various elements. This way we are removing the impurities or inclusions from the metal. This is necessary. Refining is necessary because of when we want to produce high grade, high quality, high performance ferrous alloys for critical applications such as aircraft components, automobile structural element, medical devices. Such steels are subjected to secondary refining in ladles. Okay, so secondary. By the addition of certain elements. Basically involves heating up of the metal with the using an electric arc. With the addition of certain metals, the impurities can be removed. So this is what we called secondary refining. Basically doing the refining in the ladles. So what is continuous casting? The molten metal in the ladle is poured into refractory line intermediate vessel we call tundish. So the molten metal is then tapped from the tundish, travel downward through water-cooled copper molds, and begins to solidify and is drawn through the molds at the constant velocity by rollers, which we call the pinch rolls. Prior to starting the casting operation, a solid starter bar, we also call it dummy bar, here, is inserted into the bottom of the mold. As the molten metal is first poured, it solidifies onto the dummy bar. The bar is then withdrawn at the same rate at which the metal is poured, and continues the cast metal, then cut into specific lengths by controlled torch cutting. You should guys watch the video that I send you, the link in the canvas, and you can see these things in real life, how they look like. Okay, so it is cut by torch cutting, and there is also the option, it might be directly fed into a rolling mill, so for further processing, for further shaping, such as to obtain shapes like channels, I-beams. So this has advantages like being lower cost compared to just forming the ingot and then sending it to shaping, and also continuously cast metals, they have a uniform composition and properties than those obtained with traditional ingot casting. Okay, because you are directly feeding the metal to rolling mills or other shaping manufacturing techniques. So we know steel is an alloy that consists primarily of iron with a carbon content between 0.2 and 2.1% by weight. And that's what we call steel. And alloys that have higher carbon weight, that is more than that, more than 2.1, we call those cast iron. So when we say steel, it will have a carbon content between 0.2 and 2.1% by weight. Okay. So carbon and alloy steels, these are among the most commonly used metals, and of course have a wide variety of compositions, processing options, and applications. So when we say carbon steel, we understand it has a carbon content up to 2.1%. And alloy steels, in addition to that carbon, we have one or several alloying elements such as manganese, silicon, nickel, titanium, copper, chromium, and aluminum. So a wide range of compositions depending on what type of properties we expect from the steel. In this table, we are given the different applications for carbon and alloy steels. We are also seeing 4-digit number that is given to alloy steels and carbon steels, and we're going to learn about those later, but it depends on what type of steel we have, what is the composition of certain elements or carbon. Okay, depending on the composition, steels has given different 4-digit numbers basically. And of course we are seeing that carbon and alloy steels are used for aircraft construction and automobile bodies. A lot of things you guys can see, bolts and bearings and connecting rods and springs, gears, landing gears and nuts, railroad rails, wheels, springs, we said, tubing, wire, etc. A lot of application. So as we said, various elements are added to steel. The reason basically to obtain different properties. We can change by the addition of different elements. We can change hardenability, strength, hardness, toughness, wear resistance, workability, weldability, machinability. These all depend on the composition. And of course, addition of elements can have beneficial effects as well as detrimental effects. And we are given in the table various elements that are added to steel. Generally speaking, the higher the percentages of these elements, the greater the particular properties they impart. For example, the higher the carbon content, the greater the hardenability of the steel and greater its strength, hardness, and wear resistance. On the other hand, ductility, weldability, toughness are reduced with increasing carbon content. I don't expect you to guys memorize all of these, but read through it. And certain ones that are important, just keep in mind. Such as carbon. As we see, it improves hardenability, strength, hardness, wear resistance, reducing ductility, weldability, and toughness. And chromium is important to achieve corrosion resistance in stainless steels. Keep that in mind. And the table continues here. Nickel is also common added element. improves strength, toughness, corrosion resistance, and hardenability. Silicon improves strength, hardness, corrosion resistance, electrical conductivity, but decreases machinability and cold formability. So there are some residual elements called trace elements. They may remain after refining and the processing of the steels. What are these? Antimony and arsenic, which can cause temper embrittlement. So what is temper embrittlement? I'm not sure if we discussed, but this is a form of embrittlement that is caused by segregation of impurities, in this case antimony and arsenic, to grain boundaries. It happens due to steels being tempered at certain temperature range. That's why it's called temper embrittlement. And what it does is this movement of the impurities to grain boundaries decreases toughness and increases the ductile brittle transition temperature. Of course, this makes the material brittle at higher temperatures, basically. And hydrogen embrittlement, we talked about this, so we don't want hydrogen because it can stay inside and cause porosities and therefore cause brittleness in the structure. Nitrogen can have different effects, like it can increase or decrease strength, ductility, and toughness depending on the presence of other elements. Oxygen reduces toughness. Tin causes hot shortness and temper embrittlement. I think we talked about hot shortness. So basically, some alloys separate along grain boundaries when stressed and deformed at temperatures near melting point. We call that hot shortness. Okay, so the next is designations for steels. So American Iron and Steel Institute, AISI, American Iron and Steel Institute, and Society of Automotive Engineers, SAE. These have certain designation system for steels. Okay, so the first two digits indicate the alloying elements and their percentages, and the last two digits indicate the carbon content by weight. Example, the first two digits, if it's 10, it represents carbon steels. If it's 13, it will represent manganese steels. If it's 23, it is nickel steels. I don't expect anyone to know these or memorize any of it. I'm just teaching you this so you become familiar with it. So you guys don't need to memorize anything, okay? If needed in the literature, you guys can find those easily. Basically, if you need it in the future, you guys can find these in the literature. Because if you Google it, you will see you can easily find this designation system, and you can easily understood what those 4-digit number is representing. So the American Society for Testing and Materials has another designation system. Basically, it consists of a letter and followed by 5 digits. Typical letter designations are G for AISI and SIE carbon and alloy steels, J for cast steels, for example T for tool steels, etc. So if we look at this, let's look at G41300. That is, G stands for, of course, AISI 4130 alloy steel. So if you look at 41, it means it is chromium and molybdenum steel, and the 30 is actually around 0.3% carbon. So it represents the last 2 digits, basically the carbon content, remember. And this is an example, so similar to that. You can check the other one. Okay. So as I told you guys, I don't expect you to memorize anything here, okay? Just read through and understand. That's it. So carbon steels, the principal alloying element is carbon, and only small amounts of other elements are added when we are talking about carbon steels. Of course, the strength of carbon steels increases with carbon content. Here in this table, we are seeing general mechanical properties of carbon and alloy steels. So the first 2 digits, so you guys can see in the table different properties, right? The strength, the ultimate tensile strength, yield strength, ductility, and hardness values of different types of carbon steels and alloy steels. So in this case, AISI designations are seen, and the heat treatment process is seen, and how the heat treatment processes are changing. You can guys see, as you can see, as rolled steels have higher strength values than normalized and annealed, and normalized ones have higher strength compared to annealed. Okay, so also we see AISI designations. The first 2 digit 10 that indicates plain carbon steel. Okay, so plain carbon steel, the principal element is the carbon. Okay, and the last 2 digit 20 means 0.2% carbon. Okay, so next one, for example, 1080, it is plain carbon steel and it has 0.8% carbon, for example. Okay. So the carbon steels are divided into 4 types. One is low carbon steel, or we call it mild steel, and then medium carbon steel, and high carbon steel, and resulfurized or rephosphorized carbon steel. So what are the characteristics of those? Those are important, right? So low carbon steels, these are by far the most widely used steels, and typical applications are bolts, nuts, sheets, plates, tubes, and it has less than 0.3% carbon. So machine components, usually this is for machine components that do not require high strength. So medium carbon steel has a carbon content range of 0.3 to 0.6%. And of course it is used in application that requires higher strength than that is available in low carbon steels, such as machinery, automotive, agricultural parts, railroad equipment, etc. And then high carbon steel. So this has more than 0.6% carbon, and these are specified for higher strength applications and where hardness, stiffness, strength and wear resistance is required, such as cutting tools, blades, springs, music wires, cutlery, etc. And because they are high strength, they require tempering after they are being shaped to introduce some ductility. Okay, and then resulfurized and rephosphorized carbon steel, characterized by the first two digits being 11 and 12. Basically, with containing sulfur and phosphor, basically these are phosphorus. Basically, these are improving the steel's machinability. Okay, that's it. And we also talked about the fact that the higher the carbon content, the higher the hardness, strength, and wear resistance of steel after heat treatment. So, as you can see, we are seeing in the y-axis the yield and tensile strength, how it is changing. The dashed is annealed, the solid is normalized, and normalized always have higher strength, as we talked about, compared to annealed. The difference in normalized and annealed is basically how they are cooled down to room temperatures. Basically, normalizing, the material is cooled by placing the material in room temperature and exposing to air, and it cools by itself. But when we say annealing, this is more a controlled cooling procedure. Okay, cooling rate is happening controlled way in a furnace. Okay, just to remind you guys. And then here we are seeing with the increasing carbon content, of course it defines the regions of low carbon, medium carbon and high carbon steels. And we are seeing how the tensile yield strength is increasing and ductility and toughness is decreasing. High strength low alloy steels. So in order to improve the strength to weight ratio of steels, several high strength low alloy steels, HSLA, have been developed. So these have low carbon content, less than 0.3%. They have additional alloying elements. Therefore, they have mechanical properties that are better than those of the plain carbon steels. So these can be high strength, hardness, wear resistance, toughness. Okay. So alloying elements such as chromium, manganese, molybdenum, nickel, can be added, and their combinations, of course, their combinations, or maybe one or more, etc., depending on what type of structure, what type of properties you want. So the microstructure is gonna be fine grained ferrite and as one phase, and a hard second phase, which is martensite and austenite. Okay, so they have high strength, energy absorption capabilities, but their ductility, formability, weldability inferior to those of low alloy steels, conventional low alloy steels. They are being used as the parts of truck bodies in ships, not shops. And then bridges, I-beams in buildings, etc. So I think there is something wrong with the order of the slides. This should be the next slide. So we're gonna talk about designations. Here we are seeing AISI designation for high strength sheet steel. So depending on the chemical composition, a number is designated. For example, S. S means structural quality alloys. In this case, it has carbon, manganese, phosphorus, etc. I don't expect you to guys memorize any of this, okay? And then when we see the letter X, it means the alloy has it is low alloy. It has molybdenum, chromium, copper, nickel, etc., or combination of these. So when we say W, it's weathering. Weathering means alloy has environmental corrosion resistance compared to other steels, and contains silicon, chromium in various combinations. And the formability of these sheet steels is graded by the letter F, K, and O. So F being killed, F being killed plus sulfide inclusion is controlled, K is killed, O is non-killed. Okay, so one example is given. Here we see 50xF. So 50 represents its strength, and it is X, so it is low alloy, and F represents killed plus sulfide inclusion control is achieved. Okay, so this is the way the designations are done for high strength sheet steel. So another designation scheme is used and defined by Ultralight Steel Autobody Consortium. So these we are seeing on the slide some abbreviations. It starts with some abbreviations such as BH, HSLA, high strength low alloy. So we're going to see what are these. So DP, dual phase, TRIP, transformation induced plasticity, etc. Martin stick. So for example, if we have this one, HSLA 350, 450, that means that is a high strength low alloy steel. Okay, this one here. high strength raw alloy steel with a minimum yield strength of 350. And so this first number represents the yield strength in megapascal and a minimum ultimate tensile strength of 450. Okay. Now we can look at these tables here, then it will make more sense. So this is just a table, gives us mechanical properties of some high strength steels. As now we understand how the designation is done, and different kinds of properties such as ultimate tensile strength, yield strength, ductility, and strain hardening exponent are given for these high strength steels. And this is also comparing advanced high strength steels. Here we have low strength steels, high strength steels, and ultra high strength steels, and of course their tensile strength range and how they are located in the chart, basically based on their elongations and ductilities on the y-axis. So as you can see, as the strength is increasing, the ductility is decreasing, as we can expect. For example, Martin stick steels, very high strength steels, but their ductility is low, etc. So here we have microalloyed steels and nanoalloyed steels. So microalloyed steels, they have fine dispersed particles of carbon nitride in a matrix of ferrite and perlite microstructure, and this provides an improved and uniform strength in the material. Nanoalloyed steels, as the name implies, they have extremely small grain size, so nanoscale, between 10 to the 100 nanometer. This structure achieved by special combinations of the alloying elements. And of course this is also called third generation high strength steels. So because this type of nano grain size, of course, a lot of obstacles to the dislocations, increasing the strength to a larger extent. So ultra high strength steels, these steels have an ultimate tensile strength that is higher than 700 megapascal. So there are 5 important types: dual phase, TRIP, TWIP, complex phase, and Martin stick. So these usually have applications for crash-worthy design of automobiles, and of course the drawbacks are these gonna have higher costs, higher tool and die wear, because they are very strong, right? And shaping them will cause a lot of wear in the tools and dies, and of course higher forming loads, which economically is not something desirable. So dual phase steels, they are mixtures of ferrite and martensite structure. They have a high work hardening exponent N, which improves their ductility and formability. TRIP steels, they consist of ferrite and bainite matrix with some retained austenite. And during the forming operation, the austenite can transform into martensite. So therefore they have ductility because of the austenite during the shaping, And after the forming, because of martensite formation induced by the forming process, they also have high strength. So this is interesting combination. And the next is twinning induced plasticity steels, TWIP. So as the name implies, beside the motion of dislocations, plastic deformation at certain directions is happening by twinning mechanism. And they have very high strain hardening and during formation, and it avoids necking. They have both high strength and high formability. So these combinations are not very easily attained, such as ductility, high ductility and high strength, high formability. But these steels are engineered in a way to provide us both the strength and the ductility. Okay, and the next is complex phase grades. This one has very fine-grained microstructure of ferrite and hard phases like martensite and bainite. Very high strengths like about 800 megapascal. So therefore, automotive crash consideration in bumpers and supports roof supports they are being used. Some of them have high fractions of martensite, and the strengths can go up to 1500 megapascal. Here we are seeing how advanced high-strength steels are applied in an automobile. So as you can see the percentages of alloys and structural components that are being used. And mostly it is mild steel, and some regions we use high-strength steel. So now stainless steels. Stainless steels are characterized primarily by their corrosion resistance, high strength, and ductility. And principal alloying element is chromium, which provides them their corrosion resistance, which is about 50%. So in contrast to other steels, the higher the carbon content, the lower the corrosion resistance of stainless steels. This happens because the carbon reacts with chromium, therefore it lowers the chromium content. Okay, so the stainless steel, how it forms corrosion resistance, basically the chromium reacts with the oxygen in the air and builds a protective film of chromium oxide, and it prevents further oxidation, because oxidation happens by the diffusion of oxygen and chromium, and they need to come together. Okay, but what happens, this diffusion, the oxide layer slows down this diffusion, and therefore preventing further oxidation, further corrosion happening. Okay, so where do we use stainless steel? In kitchen equipments, healthcare, surgical equipments, etc. Again, in this table we are seeing a different type of stainless steels, their properties, strength, ductility, and their typical applications are also given. And let's understand now what these AISI designations mean. So there are different types of stainless steels. So the first one is austenitic stainless steel 200 and 300 series. This is the most corrosion resistant stainless steel with 80% chromium and 8% nickel. Of course, as you guys remember, nickel being the same structure as austenite supports austenite formation. So these are the most ductile of all stainless steels and used in basically kitchenware, furnace and heat exchanger parts. They are hardenable by cold working, basically showing significant work hardening. But the bad thing about them is they are susceptible to stress corrosion cracking. Ferritic stainless steel, this is 400 series. So they have low carbon content, high chromium content and no nickel. So this means of course this is providing a ferrite phase at room temperature. And ferrite stainless steels are magnetic and they are less ductile and corrosion resistant than the austenitics. So the applications range from non-structural applications, kitchen utensils, kitchen equipment, and they are also hardenable by cold working. Martensitic stainless steel 400 and 500 series, no nickel, and they are only hardenable by heat treatment. Of course, martensite phase being hard and strong, these are strong, hard and fatigue resistant, and they are used in cutlery and surgical tools. Precipitation hardening. So these are strengthened by precipitation hardening and they have high strength and corrosion resistance at elevated temperatures. This is important because not many alloys can preserve their strength at higher temperatures and corrosion resistance at high temperatures, which makes them suitable for aerospace applications. And duplex structure. This is a mixture of austenite and ferrite in equal amounts, and their corrosion resistance is similar to that of austenitic grades. And they, on the other hand, compared to austenitic grades, they showed improved resistance to stress corrosion cracking, and this is the reason they are used in heat exchangers, pumps, wastewater treatment plants, where the corrosion is important consideration. Tool steels. These are specially alloyed, highly alloyed steels that for use. These are for use in as industrial cutting tools, dies, and molds, where it is required to have high strength, impact toughness, and wear resistance at room and elevated temperatures. Okay, so of course they are commonly used in the forming and machining of metals. So in this table we are seeing basic types of tool and die steels. Depending on the type, if high speed is required, hot work, meaning are you going to work at high temperatures, are you going to work at room temperature, cold work, whether shock resistance is required, etc. Depending on that, we have different designations and each letter is given. Okay, so if high speed is required, molybdenum base or tungsten base, M or T. In this table we are seeing processing and service characteristics of common tool and die steels, we are seeing their resistance to decarburization, cracking, hardness, machinability, toughness, resistance to softening, and resistance to wear. So all are listed. Tool steels, they are divided into major types according to the application and the composition. So we have high-speed steels. These are most highly alloyed tool and die steels, HSS. These are M and T series, as we talked about. If you go back, you see tungsten base, molybdenum base. And these can achieve hardness and strength at elevated temperatures. Other one is die steels. These are hot work H series, and they are designed to use at elevated temperatures. They have high toughness, high resistance to wear and cracking. So if we go back and look at right there, all starts with H, and depending on if it's chromium base, tungsten base, molybdenum base, it is a different number is designated. Again, to use for dies during cold working operations, we have also cold work steels. The letter is ADO series. Depending on their carbon content, alloying content, and the elements they have, how they are hardened, that is different letter is given. And of course, these are used in operations such as extrusion, forging, so they provide good wear resistance and low distortion. So the next is shock resisting steels, S series. Here. These are have high impact toughness and used in applications such as punches, header dies, where basically shock resistance is required. High impact toughness is required. So in this table, we are seeing typical tool and die materials for metalworking processes. So which process, for example, die casting, punching in metallurgy, molds for plastics and rubbers, hot forging, hot extrusion. So based on that process, which material is chosen for that process to use to make the tools and dies, basically. Of course, you guys don't memorize these things, okay? It's impossible to memorize the tables. It is just giving you information, and in your future, if you need a look for an information, you can look at these tables. So at least you guys know what do they mean and where to look at. And of course, this is the continuation of that, the same table. So in summary, we looked at ferrous metals and alloys, and different category of those, like carbon steels, alloy steels, stainless steels, and tool and die steels. We looked at steel making process and how it is important to basically refine the structure. And we looked at carbon steels and classified them and characterized them based on their carbon content. And we have seen with the carbon content, the strength is increasing. And we have looked at high strength, low alloy steels. And they have low carbon content but fine grained ferrite structure together with the second phase of martensite and austenite. And high strength steels, they provide exceptional strength and used in many applications where high strength stiffness required, such as components of automobiles. Stainless steels, main characterization of stainless steels is their high chromium content, and because it forms a chromium oxide as a protection layer, it prevents corrosion. And also we classified them, the stainless steels, austenitic, ferritic, martensitic, and precipitation hardened steels. We also looked at tool and die steels. They are said most important metallic materials, and of course they are important because they are used in manufacturing processes such as casting, forming, machining operations, where we need high speed, or we need to change the temperatures, hot, cold working, and they also need a shock resistance, right? Punching operations, etc.